what does an inverse function mean? In a nutshell, a inverse function is simply when you change the x and y values in other words, x changes to y and y changes to x. So let's take example 1. We have a data set equals 2, 4, -1, 5, and -2, 0. The symbol we use, that symbol there means inverse. It does not mean 1 over x in exponential rules. So all this means here is this. If I give you a bunch of points, the x's change with the y's and the y's change with the x. So this first one becomes 4, 2. The next one becomes 5, -1. And the last one's what? Yeah, it's just, this is the y, this is the x. Just switch them. That's all it is switch them. Graphically, so this is my point 1. This is my point 2. This is my point 3. Find the inverses of all 3 of these points. So what's the location of point 1? Nope. So it's at -3, -2. What's point 2? And then point 3? Just on the x-axis. Yeah, that line's there, but that point is there. So what's the inverse of point 1? -2, -3. So it's -2, -3. It's this point here. How about point 2? So it's at 4, -1. And how about point 3? Now, if we had more points, we'd see that the diagonal line y equals x. If you think about it, from this point, from 0, 0, if I go 5 this way, I get this. If I go 5 that way, I get that point. If I go down 1 over 4, or if I go back 1, up 4, it just switches. So these two are inverses, these two are inverses, and these two are inverses. So basically what happens is, if you want to find the graph of an inverse, draw the graph of the original function, and then fold the paper diagonally. And then whatever the dots correspond to, those are your inverse graphs. So if I had a graph that looked like this, and here's the diagonal line, y equals x. If I folded this over, I would have a graph that looks like this. I would fold it over here. So that's the easiest way, is if you have a hard time graphing equations, then just fold a page and you're there. Okay. Now, how do we find inverse functions? Example 2. First off, what's this graph going to look like? What are the x-intercepts? They both have an x. So my x-intercepts are at 0 and 5. It's positive, and both ends point up. So it's a quadratic equation that looks like this. Okay, so to find the inverse of an equation, first, switch the x and y in the equation. So in our equation, we would switch the x and y. It was originally this. So this is my first step. Second, solve for y. Because this one has two y's, I can't do it. This equation, I cannot solve for y. I could have told you this by looking at the graph. It's called the horizontal line test. If you draw a horizontal line through the graph of a function of f of x, and it crosses at more than one space, then there is no inverse. And there is no inverse. Because if we were to flip this equation, this one is not a function because it fails the vertical line test. Remember, if I draw a vertical line across it twice, it's not a function. So I cannot have an inverse function if it's not a function. So that's why I look at the horizontal line test first. If the horizontal line test fails, then I know the vertical line test is going to fail in the inverse. When this occurs, if you have an inverse of a function, f of x, then we say f of x is a one-to-one function. One-to-one, we write like this. Means for every x, there is one and only one y value for the graph. In the graph. So if it's one-to-one, it has an inverse. If it's not one-to-one, it's not going to have an inverse. So let's see an example here. Example 3. Given a function 2x minus 3, prove f of x is 1-to-1. How do I prove that it's 1-to-1? If it has an inverse, if that exists, then f of x is 1-to-1. So if I find the inverse and it exists, then I know the function is 1-to-1. First step, switch x and y. Second step, can we solve for y? So we have 2y equals x plus 3. And that's my inverse. The inverse exists. So f of x is 1-to-1. That's all you have to do. Example 4. We have a function x squared. Prove g of x is not 1-to-1. So show that the inverse of G is not what we call unique. First step, switch X and Y. Second step, solve for Y. I got square root both sides. So those cancel. And this equals plus or minus square root of X. Y has two answers. So G of X is not 1-to-1. Because this inverse is not unique. I can have a plus radical X or have a minus radical X equals the same Y value. So it's not 1-to-1. Yes, this tells me I'll have two solutions, right? Exactly. Which what we're going to see here is if you have a even power, it's not 1-to-1. Because even powers, both ends point the same direction. Yes, always. All of it, yeah, I'm glad you asked. Very, very good, very good question. All of the rules we say in the back always exist. Very good. I'm glad you thought about remember that rule. Okay, let's look at example 5. Tell me which one of these graphs are 1-to-1. Remember, if it is 1-to-1, then it passes the horizontal line test. So is A 1-to-1? Yes. Is B 1-to-1? No. C? No, it is. Because any horizontal line you draw, it's only going to hit it once. How about D? No. Very good. That's all there's to it. If you have the graph, it's much easier. Example 6. Determine whether the function f of x equals 2x minus 3 is 1-to-1, and if so, find the inverse function. So first step, switch x and y. Second step, solve for y. So 2y equals x plus 3. So the inverse is x plus 3 over 2. And it's unique, so it is 1-to-1, because there's no more than one answer. And there's the equation, there's a function. Now, because it is unique, it is 1-to-1. Example 7. We found the inverse function of that equation. Graph them. Use the same set of axes and graph the two functions. Because if it's 1-to-1, then it has to have a graph for it. Remember in chapter 1 how we drew this graph? It's a linear equation. It's got a y-intercept of -3. So at 0, -3. Slope is go up 2 over 1 and connect the dots. So there's that graph. All right. So since we have this graph, we have points. What are going to be the inverse points of it? -1, 1 and -3, 0. So here we have this graph. It's going to be symmetrical about the line y equals x. So this is the inverse graph. That's all you have to do. Once you find some points, switch them and then graph it from there. What's that? Because this one has a slope of 2 over 1. This one's going to have a slope of 1 over 2. Remember, it's just a flip because you switch x and y, so you flip the slope. This is a slope of 2. This is a slope of 1/2. This is 2 over 1. All right. Let's look at example 8. Consider the graph f of x equals x cubed plus 2. Is it 1-to-1? If so, find the inverse function and then graph them. That's this equation. Step 1, switch x and y. And then solve for y. Because that's a cube, I got to take the cube root of both sides. So this is my inverse. Okay, look at the first graph. It's a cubic equation. It's a vertical shift of 2. So the original one crosses the origin, but now I shifted up 2. The graph looks like this. This is the original function. Now we got to do the inverse function. So where it crosses at 0, 2, it now crosses at 2, 0. Got to be diagonal. So there's 2 spaces there. When x is 0, y is 2. When x is 0, y is 2. When y is 0, it's a cube root of -2. So it's 0, negative cube root of -2. There. Because it's going away from there, so it's going away from there. This is going to go towards it, so it's going to go towards it. So this is your inverse. Plotting some points will help. All right. How to prove f of x and f inverse are inverses. This is always true. The two composite functions, f of f prime inverse and f inverse of f, always has to equal x. So f of f inverse is equal to x, and then f inverse of f equals x. Let's look at the ones we did earlier. We did 3x minus 2. So the inverse there is x plus 2 over 3. Let's check to see if those are inverses or not. So we have to check both of these sides. So I take the inverse function. Anywhere I see an x, I put it in there. X plus 2 over 3 minus 2. And I do the same thing with this one. I take this equation, and anywhere I see an x in there, I put that. So it's 3x minus 2 plus 2 over 3. Work them both out. See if they both equal x. All right, so the left one. The 3's cancel. So we have x plus 2 minus 2. The 2's cancel, so we just have x. That works. Here, we'll do the top. -2 and 2 cancel. And the 3's cancel. So that means they're inverses. messy. That's how you test it. All right, so let's look at example 9. Check to see if both of these are inverses. All right. There is no calculation here because everything cancels out. There's no division or anything. It's like the 5's cancel, so we have a x minus 8 plus 8, the 8's cancel. Here, plus 8 minus 8, they cancel, so we have 5x over 5, the 5. So there's zero calculations. If it's an inverse, it's an inverse. Everything will start canceling out. There's no calculation, you have to do anything counting. And the last thing in this section, it says, if a function doesn't have a inverse, for example, if f of x equals x squared minus 2, its inverse would be, so switch and then solve for y. So we have square root of y squared equals plus or minus square root of x plus 2. We can limit the domain because what this graph looks like this. I could say the domain of this function, I only want from positive. I only want positive values. So in other words, that means here I wouldn't take the negatives. I would simply have the positives of them. So you can make a function that does not have a inverse into one by restricting the domain. And that's it for that one. Yeah, we do exponentials. Only got 3 or 4 examples.